Today in math, we've got a brief lesson in history and language, pretty much. Because sometimes, especially in the past before technology, there are certain integrals that could not be integrated using traditional techniques, such as e to the negative x squared. One of the ways that early mathematicians would start working on answering this question is they would find upper and lower bounds or upper and lower estimates for this particular integral, and then they would apply some integral techniques and be able to squeeze into the actual integral. So in this case, we just want to get used to and understand the language of what we're doing here. We're talking about upper and lower bounds of an integral that is basically the highest and lowest values that the integral could be between. In order to understand this algorithm, which is really quite simple, we just need to be able to look at a graph. So we have a graph of f of x, that's the function that's being integrated. And as you can see here, what I've done is I've drawn a series of rectangles. Each rectangle is going to estimate a portion of the area under the curve. As you can see in this situation, we're overestimating. Each of the rectangles then would have an area of 1, because by design, because we're basically going to convert this integral into a series, we want a discrete number of rectangles. Therefore, we're going to let each of the rectangles be 1 unit wide. So we start with what f of 1 is, or f of 0 is. F of 0 is 1, so we have 1 times 1. F of 1 is 1 over e, so we have 1 over e times 1. That's the area of the first two rectangles you can see. And then we have 1 over e squared. Oops, kind of lost myself there. 1 over e squared times 1. And if we're going to generalize this, recognize that 1 was the result of f of 0, and 1 over e was the result of f of 1, and f of 2, and so forth. And so really, to estimate the area that is going to overestimate the area of this integral, we're just going to take the sum as k goes from 0 to infinity of f of k. That's what we call the upper sum. Now understand, of course, we're starting from 0 because when we start with f of 0, we go up to the graph, and then we go over 1 to draw our rectangle. That's what gives us our overestimate. So to correct that, we're going to try to find an underestimate. So instead of starting at 0, we're going to start this time at 1. So that means we find f of 1 gives us the height of the rectangle, and then we go backwards 1 to create the width of the rectangle, and that creates the following series. We're basically starting with the second term and moving on forever and ever, which is essentially f of 1 plus f of 2 plus f of 3 and so on. So in other words, the sum as k goes from 1 to infinity of f of k. That gives us the lower sum. That is to say then that we can lead to this particular conclusion, a statement of the upper and lower sums. So this is the thing we're trying to integrate. Whatever the sum of this is, that's going to be the highest possible value, and whatever the sum of this is, that's going to be the lowest possible value. Notice in the notation, we have a very important distinction here. The lower sum starts at 1, and the upper sum starts at 0. That might be counterintuitive at first glance, but remember when we're looking at the picture, if we start at 0, we're going to have the largest possible rectangle, which is going to give us a larger value for our sum. Hold on a second. So be careful though, because this upper and lower sums thing is different whether a function is increasing or decreasing. Take the increasing function shown here. Again, I can't integrate it, but I might want to look at the partial sums. We have two different expressions. We can start at 1 and go backwards like we did before, and we could start at 0 and go forwards like we did before. That creates two different partial sum expressions, one starting at 1 and the other starting at 0. Clearly, when you look at the graphs of this increasing function, this time when I start at 1, I'm getting the larger numbers, and when I start at 0, I'm getting the smaller numbers. So this is the statement of partials, or expression of partial sums here, and notice the difference. We started at 0 and then 1 to get the lower and upper boundaries, respectively. Leading us to the final conclusion that if f of x is an increasing function, then we find our lower and upper sums, going from 0 to 1, and if f of x is a decreasing function, we go from 1 to 0. rather than trying to memorize this, which I wouldn't try to do given the amount of information you have to learn, rather than try to memorize this, I would just remember that partial sums are determined by whether we're increasing or decreasing. Definitely use your technology. Definitely make a graph of the function before you state your partial sums to make sure that you're stating your sums correctly. Hope this was helpful. Thanks. Oh, sorry, one last thing before I sign off. I will say, too, sometimes they might give you a function. In this case, this function is not integrable either using traditional methods, but sometimes they'll give you a function that is integrable, but they'll ask you to estimate the upper and lower sums anyway, in which case what you'll have is a series here on the right and a series here on the left that can be summed to infinity. Fortunately for us right now, the only series that we can sum to infinity are geometric series. So if you recognize exponential decay or a geometric series exists here and here, then you can evaluate using the summation of infinite series. So again, I hope this is helpful. Have a great day.